At the end of the 19th century, physics consisted essentially of classical mechanics, the theory of electromagnetism, and thermodynamics. Classical mechanics was used to predict the dynamics of material bodies. Maxwell's electromagnetism was used to provide the proper framework to study radiations. The matter and radiation were described in terms of particles and waves respectively. Thermodynamics was used to explain the interactions between matter and radiation. The overwhelming success of classical physics, classical mechanics, classical theory of electromagnetism, and thermodynamics made people believe that the ultimate description of nature had been achieved. It seemed that all known physical phenomena could be explained within the framework of general theories of matter and radiation. At the turn of the 20th century, however, classical physics was seriously challenged on two major fronts: relativistic domain and microscopic domain. Einstein's theory of relativity showed that the validity of Newtonian mechanics ceases at very high speeds. With the development of new experimental techniques to the point of probing atomic and subatomic structures, it turned out that classical physics cannot provide the proper explanation for several newly discovered phenomena. It thus became evident that the validity of classical physics ceases at the microscopic level, and that new concepts had to be invoked to describe the structure of atoms and molecules and how light interacts with them. Classical physics failed to explain several microscopic phenomena such as black body radiation, photoelectric effect, atomic stability, and atomic spectroscopy. The first breakthrough to explain the microscopic phenomena came in 1900. In 1900, Max Planck introduced the concept of quantum of energy. While explaining the phenomena of black body radiation, Max Planck postulated that the energy change between radiation and its surroundings takes place in discrete or quantized amounts. He argued that energy exchange between an electromagnetic wave and matter occurs only in integral multiples of hf, where f is the frequency of the wave. He called that hf is the energy of a quantum. Planck's idea gave an accurate explanation of blackbody radiation. Planck's idea prompted and triggered an avalanche of new discoveries. In 1905, Einstein provided a powerful consolidation to Planck's quantum concept. Einstein was trying to understand the photoelectric effect when he recognized that Planck's idea of quantization of electromagnetic waves must be valid for light as well. So, he suggested that light itself is made of discrete bytes of energy called photons. The energy of each photon is hf, where f is the frequency of the light. The introduction of the concept of photon enabled Einstein to give an elegantly accurate explanation to the photoelectric problem. It was first accurate explanation of photoelectric effect ever since its first experimental observation by Hertz in 1887. Another breakthrough was due to Niels Bohr. In 1913, Bohr introduced his model for the hydrogen atom. In his model of hydrogen atom, Bohr argued that atoms can be found only in discrete energy states. The interaction of atoms with radiation takes place only in discrete amounts of energy. Bohr's work provided a satisfactory explanation to several problems such as atomic stability and atomic spectroscopy. In 1923, Compton made an important discovery that gave the most conclusive confirmation for the particle aspect of light. By scattering X-rays with electrons, he confirmed that the X-ray photons behave like particles with momentum hc over lambda. This series of breakthroughs due to Planck, Einstein, Bohr, and Compton gave both the theoretical foundations as well as the conclusive experimental confirmation for the particle aspect of waves. They confirmed the concept that waves exhibit particle behavior at microscopic scale. At microscopic scale, classical physics fails not only quantitatively but even qualitatively and conceptually. In 1923, de Broglie introduced another powerful new concept that classical physics could not reconcile. He postulated that the material particles themselves display wave-like behavior. This concept was confirmed experimentally in 1927 by Davison and Germer. They showed that interference patterns can be obtained with material particles such as electrons. Although Bohr's model for the hydrogen atom produced results that agree well with experimental spectroscopy, it was criticized for lacking the ingredients of a theory. Like the quantization scheme introduced by Planck in 1900, the postulates and assumptions adopted by Bohr in 1913 were quite arbitrary and do not follow from the first principles of a theory. The dissatisfaction with the arbitrary nature of Planck's idea and Bohr's postulates prompted Heisenberg and Schrödinger to search for the theoretical foundation underlying these new ideas. By 1925, their efforts paid off. They skillfully combined the various experimental findings as well as Bohr's postulates into a refined theory called quantum mechanics. This theory provided an accurate reproduction of the existing experimental data. This theory turned out to possess an astonishingly reliable prediction power, which enabled it to explore and unravel many uncharted areas of the microphysical world. This new theory had put an end to 25 years work patchwork which was dominated by the ideas of Planck and Bohr and which later became old quantum theory. Historically, there are two independent formulations of quantum mechanics, matrix mechanics and wave mechanics. Matrix mechanics was developed by Heisenberg to describe atomic structure starting from the observed spectral lines. Heisenberg was inspired by Planck's quantization of waves and by Bohr's model of the hydrogen atom. Heisenberg founded his theory on the notion that only allowed values of energy exchange between microphysical systems are those that are discrete, called quanta. He expressed the dynamical quantities such as energy, position, momentum, and angular momentum in terms of matrices. He obtained an eigenvalue problem that describes the dynamics of microscopic systems. The diagonalization of the Hamiltonian matrix yields the energy spectrum and the state vectors of the system. Matrix mechanics was very successfully in accounting for the discrete quanta of light emitted and absorbed by atoms. Wave mechanics was developed by Schrödinger. It is a generalization of the de Broglie postulate. This method is more intuitive than matrix mechanics. Wave mechanics describes the dynamics of microscopic matter by means of a wave equation called Schrödinger equation. Instead of the matrix eigenvalue problem of Heisenberg, Schrödinger obtained a differential equation. The solutions of the Schrödinger equation yields the energy spectrum and the wave function of the system under consideration. In 1927, Max Born proposed his probabilistic interpretation of wave mechanics. He took the square moduli of the wave functions that are solutions to the Schrodinger equation and he interpreted them as probability densities. These two are ostensibly different formulations, the Schrodinger wave formulation and Heisenberg's matrix formulation, were shown to be equivalent. Dirac then suggested a more general formulation of quantum mechanics which deals with abstract objects such as cats, bras, and operators. The representation of Dirac's formalism in a continuous basis gives back Schrödinger's wave mechanics. The representation of Dirac's formalism in a discrete basis gives back Heisenberg's matrix formulation. The approach of Schrödinger represents the wave formulation of the general theory of quantum mechanics. The approach of Heisenberg represents the matrix formulation of the general theory of quantum mechanics. In 1928, Dirac combined special relativity with quantum mechanics and derived an equation which describes the motion of electrons. This equation is known as Dirac's equation. Dirac's equation predicted the existence of an antiparticle called positron which had similar properties but opposite charge with the electron. The positron was discovered in 1932, 4 years after its prediction by quantum mechanics. In summary, quantum mechanics is the theory that describes the dynamics of matter at microscopic scale. Quantum mechanics is the only valid framework for describing the microphysical phenomena. Quantum mechanics is vital for understanding the physics of solids, lasers, semiconductors, superconductor devices, and plasmas. In short, quantum mechanics is the founding basis of all modern physics such as solid-state physics, molecular physics, atomic physics, nuclear physics, particle physics, optics, thermodynamics, statistical physics, and so on. It is also considered to be the foundation of chemistry and biology.